Hello everyone, my name is Viraj and today we'll be discussing the 29th problem from the CP-31 sheet by TLE Eliminators under the 800 rated questions. Let's go. So I'll be moving on to my CP-31 sheet over here, ticked off the 800 rated parameter, and I will open up my 29th problem. Everybody likes good arrays. Alright, so we'll try to read this problem first. Okay. An array A is good if all pairs of adjacent elements, that is ai and ai plus 1 from I greater than equal to 1 less than n are of different parity. Alright, so we'll understand what does that term mean. Note that an array of size 1 is trivially good. Okay, trivially good. Now you are given an array of size n. In one operation you can select any pair of adjacent elements in which both elements are of the same parity. You delete them and then you insert their product in the same position. You have to find the minimum number of operations to form a good array. Alright, we have read the problem. Let's try to generalize what are they asking us. Okay. So of course they have said over here that I have an array A where I have the numbers. You can say this is A1, then I have the number A2, I have the number A3, A4, this is A4 dot 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 till I have the numbers. You can write AN. And this is an n-sized array. Alright. Now what are they saying over here is they are saying that we effectively want this array to be good. And this array to be good means every adjacent element pair, that is, if I can mark this with a blue pen, these two are adjacent elements, then these two are adjacent elements, these two are adjacent elements, so on, so on, so on. Every two adjacent elements, A1, A2, A2, A3, A3, A4, so on, are of different parity. So this is a very important term. What do we mean by parity? So parity is actually nothing. It's just a meaning of representation when you say what is the nature of a number in respect to odd and even property. Alright, if let's say the number is odd, if let's say the number is even, whatever nature it contains with respect to this odd and even nature, it's basically called the parity of that number. So now, coming back to the problem, if I say that I want adjacent elements to have different property, that means, for example, if let's say I take up these two pairs, this is A1, A2, then these two numbers as a pair, A1, A2, then if let's say, assume that A1 was having an odd nature, that is the parity of A1 was odd, then parity of A2 has to be even. That is different parity. Or if let's say A2 had an even parity, then A1 had an even parity, then A2 will have an odd parity. Both cannot have the same parity, that is both cannot be odd or both cannot be even. Alright, so very very simple. Parity is again the general representation idea when we talk about the nature of any number with respect to its odd and even property, and that parity that is termed in our coding language, we actually term that thing. And using this parity concept in this problem, what they are saying is we want different parity of the adjacent elements. So as I repeated again, A1, A2, if let's say you have one as odd, one as even, or one as even, one as odd, both cannot be odd, both cannot be even. It's a different parity, that's by basic common sense. Alright, so now we want the whole array to be good. Okay, now what's given to us? Of course, this array has to become good. It's not initially good. To make it good, you have been given an operation to perform. This is something, it's sort of a power or an operation you can actually do. And this operation, what does it state is, if you select some pair of adjacent elements in which both elements have the same parity. For example, I just selected some random element ai and ai plus 1. Alright, let's say just one element ai, and let's say the next element it came to it, ai plus 1. Then if let's say their parity are same, that is if let's say both are of even parity, let's say EE, or let's say both are odd. If let's say this happens and both have the same parity, then you can delete them and then insert their product in the same position. Alright, so if let's say I have an array generalized, let's say A1, A2, A3, A4, so on. If let's say assume that these two numbers had the same parity, let's say odd, both of them were odd, then what I can do is I can take A1, I can take A4, and in place of A2, A3, just delete them, and I can place their product, that is A2 into A3, as a singular element over here. This is one operation. Doing this is one operation. Okay, doing this is one operation. I hope this is clear. Now what they are saying is, by using this operation, tell me what is the minimum number of operations you can do to make your array good. That is, Finally, every adjacent element pair is having a different parity. That operation count, I can call this, let's say, min op, all right, min underscore op. This is something that we want to print or that we want to calculate. Okay, so this is the whole problem. Now, let us look at some test cases and understand what is happening over here. All right. So let's just say that you have a test case 1, 7, 11, 2, and 13. Okay, so I'll take the first test case. This is 1, 7, then you have 11, 2, and 13. So I'll write down the parity first. Okay, this is 13 by the way. This is 13. So I'll put a comma over here. These are the 5 numbers. N is given 5 to me. So the parity over here is very clear. This is odd nature, this is odd nature, this is odd nature, this is even nature, this is odd nature. Now what I can do is, I can do something like this. Let me take these two elements. These two elements have odd nature, so same parity. Let's multiply them and insert them back. So deleted 1 and 7, multiplied 1 and 7, you got a 7, and you inserted 7, 11, 2, and 13. Now let's note their parities again. This is odd, odd, even, and odd. So I still am not good to go. I can catch up these two elements again. Both of them are odd, have the same parity, multiply them and insert back their product after deleting them. So I have something that looks like 77, 2, and 13. Now if I write their parity over here, this is odd, this is even, and this is odd. Now if you take up any two adjacent elements in this, let's say you take up these two elements, or let's say you take up these two elements, can I see that they have different parity nature? Of course, one is, let's say, one over here is, let's say, odd, then other is even, and then if, let's say, you talk about the other pair, one is even, one is odd. So you are good to go. Can you term this as a good array? Of course, I can term this as a good array. And then if you can actually term this as a good array, consider how many operations did you do. We did one operation to combine 1 and 7, and then we did one more operation to combine 7 and 11. So you did 2 operations total, and this becomes your answer. So over you can see sample output was 2. Alright, so a very, very easy problem to understand. What are we trying to picturize? What are we trying to do? So now, if you pick your pen and paper, you can pause the video, give this problem a try, and you will be able to figure out the rest of the 2 cases. Alright, so let's move ahead. Let's actually talk about now a very important idea before actually deep diving into the main solution. If I want to create a solution initially, what is my expected time complexity? Very important. Alright, why is that needed? Because I want to remove all the redundant ideas I could have created which might fetch me a TLE. So by generalization, by general fact, I know that I have 1 second giving me 10 power 8 elementary operations as a limit. This is something I'm allowed. Now I know in this question, there is a time limit for each and every test, which is 1 second. So if I write over here that one test is basically allowing you 1 second, which is basically allowing you 10 power 8 operations. So this is good to go. But every test has some test cases, right? If you look over here, every test has some test cases, which is actually this t value, that is 500. That means if I ask you what's the number of operations you can perform for each and every test case, this is something written as 10 power 8 upon 500, which is 1 by 5 into 10 power 6, or very acutely, this is 2 into 10 power 5. Elementary operations per test case. Now this is very important because if I look at n over here, assumingly that n would be the main factor of the dependent factor which would come in the time complexity when I finally calculate for this problem, I can take that if n is in 100 order, can I create a solution that's n cube? Definitely not, because n cube means I'm going in 10 power 6 order and I wanted something in 10 power 5. So if this is sort of somewhere my limit, you can say, I know I can create anything below this. So if let's say I create something like an n square or maybe O of n or anything, let's say to a constant limit, I'll be good to go. Yes, all of this might work. But if I go in a light boundary of n cube, I'll start getting a TLE, because even if I create a good solution, even if it is logically correct, it will fetch me a TLE, it will not fetch me an accepted solution. So I need a solution that runs in n square order or something below that, if preferable, right? And this is where my main idea strikes, that okay, redundant ideas that could have gone in higher complexities of n cube order should be removed. I should only think of orders where I can create solutions less than equal to n square or somewhere in that order. Alright, so this is our expected time complexity discussion. Now that we realize that, okay, what sort of a solution am I looking at? I know I can start off with some problem discussion in my head. Maybe I can fetch up a good solution, maybe in O of n, maybe in n square, maybe I'll be good to go. Alright, so let us begin. What should be my initial idea in this problem? So first of all, when we talk about parity over here, we have to understand very important thing. If I am talking about two elements, I am deleting them and I am inserting them back, it's a very viable question to ask that if you start off with these two elements, let's say I have this element E1 and the element E2, you basically delete them, assuming that they have the same parity, and you insert again an element back, that is E3. Now remember, when we saw the sample case over here, once I deleted 1 and 7, I asked myself again that the new numbers parity, was it odd, was it even? I asked this to myself. Now I don't want to simulate this process, but rather if I know some mathematics pre-hand, maybe I can get this very intuitively what happens when I finally simulate the main problem. Meaning, we know by fact, I can write this down by proof over here. If let's say case number 1, E1 and E2 have the same parity, by the way. So E1 and E2 both are odd nature. So let's take an example. Let's say E1 and E2 both have an odd nature. That means they are of the format 2k plus 1. That is how we generally represent odd numbers, k being a whole number representation. And then you multiply that with, let's say let's say this is 2k1 plus 1, then you can write this as 2k2 plus 1, something like that, where k1 and k2 basically are whole numbers in the range of integer line. And 2k plus 1, 2k plus 1 is the general representation of an odd number. So I've taken for E1, it's 2k1 plus 1, and you can write for E2, 2k2 plus 1. Now, if you multiply these two, that is the product that I'm taking. If you do that, you basically get something like looks like this: 4k1 k2 plus this is 2k1 plus this is 2k2 plus this is 1. Now, a very important point of this new number, that is basically element 3, is this number is still odd. Because if you multiply, if let's say I want to divide this by 2, then this 2 will get distributed over here, will get distributed over here, will get distributed over here, but this plus 1 is being a problem, right? This is going to make the parity of this E3 number actually as odd. What does that tell me? By general mathematics, it tell me that this number is still odd, which means an odd number multiplied by an odd number gives me an odd number. This is case number 1. Point number 1. Now, even going further on this part, case number 2 would be if let's say E1 and E2 both had the same parity and both were even. So same case generalized, I'll say okay, E1 was of the nature 2k1, that's basic, 2k1 is the general representation of an even number, and then you have multiplied as 2k2. You of course get over here as 4k1 k2, and isn't this number divisible by 2? Of course, if you write this by 2, this 2 and 4 gets cancelled, which means this is fully divisible by 2. That means this new number E3, which would have gotten by multiplying two even numbers, is actually even. So this tells me that even into even gets me an even number. Now the argument is, why did I discuss this part? Okay, why was this even useful? Let's go back. Let's see one thing very, very importantly. Over here, initially the array is not good. That's correct. And I finally want to make the array good. Let's understand effectively if an array is good, what should it look like? If you say that your array is good, effectively it should look either of these two cases. That is case number 1. If you want adjacent parities everywhere, that is basically you're trying to alternate the parities. So the array would look something like this: odd number, even number, odd number, even number, odd number, so. Or it can look of this case, this variety: even number, odd number, even number, odd number, even number, odd number, and so on. These are the only two viable cases where you actually term the array to be good. It's common sense, right? Try to understand this. If you're talking about every two adjacent elements having the different parity, that means if let's say you start off with the first two elements having the different parity, odd and even, then the next two elements parity, as in the third element, should have the parity odd, because then if you take these two elements for even and odd, it will not fulfill the condition if this is not odd, this is of even nature. Makes sense? And that whole idea of propagating even and odd is going to go to the very end of the array, which would basically mean that the good array by definition is actually an array which has alternating even odd parities. So either you have case number 1 where you start off with an odd and then you go odd, even, odd, even, odd, even, or you start off with an even and you go odd, even, odd, even, odd, even, odd. These are the only two cases. But the catch over here is your initially array is not good. So what it might look like, let's try to understand. For example, the array initially, this is case 1, this is case 2 of what we want to achieve, either of the any case. And actually in your initial condition, the array might look somewhere like this. It might be having some odd elements, let's say some even elements. then some more odd element, then let's say an even element, then let's say some more odd elements, then let's say an even element. So this is just an example, right? I have just noted down the even and odd nature of the array. This is what my array initially will look like. All right. So we want that this array goes from this to look something like a good array. Now observe over here this very, very crudely. You want odd evens to alternate. If I want my operation to be executed, I can only take adjacent elements which have the same parity. Over here, the same parity elements adjacents look something like this. This is adjacent and have the same parity. Fine. This is adjacent, has the same parity. Okay, great. Does these two elements being adjacent but have the same parity? No. This is odd even. Of course, no. Okay, this is not possible. So let's just focus once over here. These two elements are adjacent. These two elements are adjacent. They have the same odd nature. We go back to our property number 1. We said that an odd number into an odd number gives you an odd number. So I'm not talking about the case where I go into the values. Just assume that you had these 3 odd numbers in a line. What can you effectively do? Can I say that I would have taken these odd numbers, multiplied them, and then I would have gotten some other one more odd number effectively, which would have made 3 odd numbers go down to 2. Now I would have taken these 2 odd numbers, multiplied them, effectively again gotten an odd number, and now I have one odd number, that is O. Let's look over here. Take these 2 even numbers, same idea over here, take these 2 even numbers, multiply them, get back an even, write an even. Take these 2 odd adjacents, get back an odd, write it. Only one even, not an issue, cannot do anything, one even. Take these 3 odd numbers, effectively you would do 2 operations and make a single odd number out of them. And this final even, this can be copied as it is, you have an even. Now look at the final case of the array. Odd, even, odd, even, odd, even. Did you not get a case that looks something like this? Yes. So effectively, what did I identify? If I have a segment of same parity of elements, if I have a segment, I'll write this on a new page. If I have a segment of elements of same parity, then I want to reduce them, you can say reduce them to a single number by how many operations? If let's say this segment length is S, then basically you can say by S minus 1 operations. This is the whole idea behind the problem. Understand this once more. You had some odd elements, you had some even, then some odd, then some even, then some odd. Effectively you want alternate odd, even, odd, even, odd, even, or if effectively you want alternate even, odd, even, odd, even, odd. So you want a segment of odd elements to finally club itself together to a single odd element. Similarly, you want a segment of even elements to club itself together to a even single element. To do that, we utilize the property that irrespective of the value, I'm not talking about the value, just multiplying 2 odd numbers gets me an odd number, and just multiplying 2 even numbers gets me an even number. So if I say that I have a segment of S size, that is, if over here you observed, you had 3 odd elements, to make 3 odd elements go into a single odd element, how many operations did you do? 3 minus 1? Of course, because you will take 2 pairs directly and effectively get new odd numbers, making your final odd number fetch up in exactly S minus 1, or in this case 3 minus 1, that was 2 operations. So you did 2 operations over here, you did 1 operation over here, you did 1 operation over here, you did 0 operations over here, you did 2 operations over here, and you did 0 operations over here, which effectively meant that your net count of operations was 2 plus 1 plus 1 plus 2, that is over here 6. Am I right in this? Yeah, 6. So can I say that if your assumed array was given in somewhere in this sort of a manner, where I'm not about the values, just consider with the parity, I would require 6 operations to make it something that looks like a good array. That is the first case, and then second case is automatically viable. If you had some other scenario where you could have also get the second case, it's basic common sense to understand that stuff also. Alright, so this is the whole idea of the problem, that all I have to do is effectively every segment identification has to be done, and that segment's length, if considered, is S. I would be performing s minus 1 operations. Now, when I want to code this up or when I want to implement this, the other way of identifying this is if let's say I get two adjacent elements to have the same parity, what do I want to do? I want to perform an operation. Over here, realize, if let's say you had two adjacent elements odd, you performed an operation, you got a 1 odd. Now if let's say you would have two adjacent elements again, you would have performed effectively one more operation and you would have gotten this range. So effectively, I can write one implementation can be you identify what is the segment length. Let's say this is segment length s. So you add s minus 1 to your answer. That can be a bit more complicated. Again, different implementation technique. What I am suggesting is understand this. What you can simply do. You can say if my current element, that's a of I, modulo 2 is equal to a of I plus 1 modulo 2. That means two adjacent elements have the same parity, then I know I want an answer plus plus. Why? Because this means if let's say you have these two adjacent elements, you want to reduce them to a single element. So you would be performing an operation. Next time you get two more adjacent elements to have the same parity, effectively you would be performing that operation to reduce that into a single element. So that gets counted more. So you in this segment will check that condition of the same parity adjacent twice, and that would increment your answer only by 2, which was indirectly saying I counted the segment's length as 3 and I incremented 3 minus 1 in my answer, that was effectively 2. So that's one other way of figuring out the problem. Alright, again, as I said, implementation difference. If you get the logic, you can implement this in any way how you like. I just wanted to have an implementation where I take up a direct approach of addressing the adjacent elements and adding on my answer, because that effectively makes much more sense. It's going to give the same answer as I would have counted the whole segment length as s and added s minus 1 to my answer. Alright, so this is the main idea. However you implement this in code, that's totally up to you. Alright, so let us move on to our coding part finally to understand how do we picture this out. So this is my problem solution. I have done something like this. I first take the input of t, very basic, take the input of n, take the input of the array. So up till here, all I'm doing is taking inputs. Then I have a variable over here that is operations count, and then I run a loop from 0 to n minus 1. Why n minus 1? Because, or less than n minus 1, because I want to go to I plus 1 index. So I plus 1 index existence should be there. If I go till less than n, then I know I plus 1 will not exist if I go out of bounds. So I check over here is the parity, that's a of I mod 2. Basically that means what is the nature. So a of I mod 2 is basically going to tell me odd or even nature. If this odd or even nature of ai is equal to the odd and even nature of ai plus 1, that means two adjacent numbers have floated up the same parity. Increment your operation count by 1. And then when you come out of this loop, simply print your operation count and this gives you the correct answer. What do we think is the time complexity for this? Of course, I have a simple n loop over here that runs in n order to take the input, and then I have a simple n order loop over here also to find the main answer. Then this is a simple relation check. This is a constant time check over here. So effectively my time complexity is, you can write O of n, which is very nice for me because I have created a solution that is basically O of 100, and I wanted a solution that's less than 2 into 10 power 5 if you remember. So I'm good to go in this area. And what about space complexity? Again, dependent on the size, that's the array size, that's O of n again, so O of 100. Well, within my boundaries, I'm going to get an accepted solution, not a TLE at all, since my logic is right. Alright, so this was all about the problem. All we had to identify was the odd even parity nature and this multiplication technique of where odd and odd gives you an odd again and an even gives you even again. And then realizing that, okay, the segments had to effectively boil down to a single element of that particular parity. So that is s minus 1 as an answer. Either I can have an iteration technique where I can count and reset and get the s length. So s minus 1 is added to my answer every time. Or I can do this sort of a trick over here where I just take adjacent elements, parities check. If they have same parity, that effectively would have simulated to add an operation to my main answer. Alright, so that brings us to the end of our problem. I hope you like the video. Thank you for watching.